Does anyone have any questions about any of the questions I assigned yesterday you'd like me to go over? Start with these ones, the 11 to 18. Anything there anyone wants me to take a look at? These three were power. These ones were all work-related, change in energy. 15. Okay. A 4-kilogram rubber ball drops from a height of 5 meters to the ground and bounces back to a height of 3 meters. How much potential energy does the ball lose on the trip down? How much does it regain on the trip back up? So on the way down, you're looking just potential energy is just going to be mgh. So it's just going to be 4 times 9.8 times 5. And this will be the loss, right? Because the final is 0. Initial will be this height. So then this, whatever this value is, that's going to be 20 times 9.8, which is what, 196? Please have 196 been on the list. There it is. Yeah, 4 times 5 is 20. 20 times 9.8 is 196. Then on the way back up, you're gaining potential energy. So initial will be 0 at the ground level. Final is going to be mgh for a height of 4 times 9.8 times 3. So that's 12 times 9.8, which is going to be 18 point something? 117.6. So then the net loss in potential energy is just the subtraction of these two. So what is that? 79? 78? Something like that? 78.4. Does that kind of make sense, fine? Okay. Anybody else? Questions on this page from the stuff I assigned yesterday? Okay. These ones were substantially more gross. The spring ones are always a little bit more interesting, just the way they're worded. Questions, comments, concerns about the spring questions. Anyone have a chance to look at these? I didn't have the answers to all of these. I do have some of them that I've worked out in previous semesters that students had questions on. Are there any comments, questions, concerns on these guys? Some of the answers I had, question 5. I didn't actually finish the value for that one. Number 5, I got 22.5. joules. Question 7, I had a value for as well. 7, I got 0.0968 joules. Oh, nope, that's not true. Sorry, my bad. That's part of the work. The final answer for this one is 0.2232 joules. Number 8, I had a value for as well. What is the spring constant? I got 9,600 newtons per meter. Okay, equals that. So I had a few values for these that students have asked me to work out in the past, but those are the only 3. Are there anything there anyone wants me to look at? If you haven't had a chance to look at the spring ones, you definitely want to do that. Alexis, you really look like you were just about to say something. Okay. Here day? Sorry? Okay. This one's just a graph. Finding the area there. The force used to stretch a spring, how much work is required to extend the string by 0.6 meters? It's just this area. Which is, yeah. Can I do what? Yeah, rip it out and hand it in. Yeah, just pop it straight out. Okay, then if there are no questions about these, means you're either all amazing, which would be cool and totally believable. I'm not being sarcastic. I believe that you can all do these. Or, also believable, we haven't looked at them yet. So, do have a chance. Please do take the time to take a look at those if you haven't already. If you have and you're confident with them, great. Tomorrow's lab will depend on your understanding of springs in a big way. Because you're bungeeing tomorrow. Oh, we're going to start that process tomorrow. Okay, find me this page. If you're ready for it, flip to here. If there are no other questions. We're going to look at something called the work energy theorem, and it is related. The equation is the same as what we've looked at already. How we interpret that equation is going to be slightly different. So the work energy theorem, I've already kind of defined it for you, starts here. The way we define work, one of the ways we define work was that work is equal to a change in energy. Well, this expression, we can rewrite it. Change in energy is just energy final minus energy initial. And we can just rewrite this guy. We can add energy initial over to the other side where it belongs at the beginning. And we're going to get something that looks like this. Energy initial, whatever the starting energy of your system is, plus whatever work gets done, either on the object or to the object, is going to equal your final energy. And this guy here, this formulation of this equation is what we call the work energy theorem. And I think it makes sense. The initial energy plus whatever work is done, either positively or negatively. You can do work to an object or you can do work on an object. Is going to be equal to whatever your final energy of the system is. And these guys, these two energies, can be a combination of any of the energy types we've looked at already. These could be kinetic, they could be potential gravitational, they could be potential spring. And then this work is going to be done by, could be an applied force, could be friction. Those are generally the two that are going to do work related to the objects in the question. Friction is going to take energy out. Generally speaking, an applied force will put energy in. But this boxed equation is what we refer to as the work energy theorem. So imagine, if you will, a large rock inside a tall vacuum chamber. If you've never seen a vacuum chamber before, what a vacuum chamber is, it's what it's in the name. It is a chamber in small shapes. It's I've seen them about yay big. It could fit on the tabletop here. And it's a vacuum. All of the air, as much of the air as the pump has strength to pull out, all the air has been pulled out. The biggest vacuum chamber I've ever seen was something like, I want to say it was 10 stories. Like there's one out in, I don't remember where it is, but I think it's a 10-story vacuum chamber, and they're able to suck all of the air out of this vacuum chamber. Takes a couple hours to do, but once they've done it, it's a big cylinder. It's a large room. It might be about this big around, our classroom around, and 10 stories tall. And they're able to pump all of the air out of it, and then they drop stuff, or they see how things behave. It's a lab. In one of these systems, a rock released at the top of the chamber, or is held at the top of the chamber, and it falls. Or the video that I've seen of this, the massive chambers, it's a bowling ball. They've got a bowling ball and a feather, and they release them both at the same time. For an object falling, we know the acceleration is going to be 9.8 meters per second squared. As it falls, the reason we want this thing to be a vacuum chamber is, what does the vacuum, if there's no air, the vacuum chamber is going to allow for what? No air resistance. So as it falls, we've got an object up at its highest point, and it's going to start to fall towards the bottom of the chamber. As it falls, what happens to the potential energy? It decreases. Potential energy is mgh, goes down. Its kinetic energy as it falls is going to do what? It increases. The object is getting faster due to the acceleration of gravity, so its kinetic energy is going up. So as the potential energy goes down, the kinetic energy goes up. And is there going to be any energy lost in this vacuum chamber? No. No energy is lost. Because there's no air resistance. How does air resistance pull energy out of the system? How would air resistance or change the energy available to the system? Yeah, it creates friction on the object that's falling, and it creates heat energy to that object. The most extreme example of that would be like a spacecraft re-entering our atmosphere. Obviously, we have an atmosphere. A spacecraft is moving relatively quickly, and they heat up like crazy. I don't think you guys were alive for it, but there was for example, the examples are always bad. There was a space shuttle. I was alive for this. Actually, it happened during the day. A space shuttle was re-entering. It was Columbia. Was re-entering, and on takeoff, its heat shield had been damaged. And NASA was aware. They saw it happen and didn't tell the astronauts. And then Columbia re-entered, and so much heat was generated that it vaporized the space shuttle. And the people inside were lost. But that's the kind of insane amounts of heat get generated and pulled out, and that's part of what slows these things down, is the amount of heat that gets generated due to air resistance. So it's something to consider. We don't think about it very often. If you're playing catch out on the field at lunchtime, you don't catch the ball and it's not flaming hot. So your guys' experience of air resistance is pretty minimal as far as the energy that it's pulling out. But on larger scales, it's really quite impactful. In this case, though, vacuum chamber, nothing's lost. So because of that, the law of conservation of energy. We've talked about the law of conservation of momentum. Now here's the law of conservation of energy. It states that no energy can be created or destroyed. Only transformed or transferred. And so if you are losing energy, and so when we talk about the no energy became created or destroyed, only transformed or transferred, it's important to add this little caveat within a closed system. And so what this means is if energy is leaking out somewhere, it means your system isn't big enough. You haven't considered all of what's in the system, and you need to figure out how can you expand the system to include the missing energy. So in real life, most situations involve air friction, and as a result, some energy is always lost. And in the examples that we're going to look at, it's more than just air friction. There's going to be friction everywhere. And as a result, energy is going to be lost. This is the whole premise behind roller coasters. If you were able to ride a roller coaster in a vacuum chamber, which would be interesting in of itself, and perfectly lubricate the roller coaster would never end. if you were able to eliminate friction and air resistance, unless you chose to brake, that roller coaster would just keep looping forever, which could be awesome for those of you who like roller coasters. Friction has a huge impact on lots of different systems. So because friction and air resistance are a thing, energy is lost, and we look at this as work being done. So this work term is going to be, I have said it already, is either an applied force or friction, or air resistance shows up there too. So when energy is lost, it's leaving the object, whatever it is you're looking at, as one of two things. It's either leaving the object as heat, or it's leaving the object another way. If you took out all of the air from a vacuum chamber, you're not just removing a source of air resistance, you're also removing another source. Does anyone else know what you're not getting if you have all the air gone? There's a tagline from a movie. I think it was from Alien. Has anyone seen the movie Alien? Okay, well the tagline is, it's a horror movie. The tagline is, in space, no one can hear you scream. Because sound requires a medium to travel through. If you pump all of the air out of a vacuum chamber, you're not going to have any sound either. And so energy leaves as heat or sound. I mean, it says we can rewrite the law of conservation of energy to include work, but I kind of already did that. Energy initial plus work is equal to energy final. Where this is the work added, or sorry, nope, energy added, or removed by something. So, and this is it. This is, today's lesson is just going to be a bunch of examples of how to apply the work energy theorem to a bunch of different scenarios, and then we're done. So an example would be something like this. You're on a roller coaster. For those of you who enjoy roller coasters, don't worry, Lena, everyone survives the roller coaster. Here you are. Everyone survives the roller coaster. Yes, we did talk about the euthanasia coaster, didn't we? I want you to draw several locations. If you're truly enjoying the roller coaster, the arm's got to be in the air as you go down. As you reach up, as you reach the top of the hill, you're going back. You're living the dream. You're loving the roller coaster. So there's all sorts of language that's going to be here, or it's going to involve the roller coaster. Typically speaking, the way roller coasters are designed is that there is one biggest peak. And if the roller coaster, if it just, like, you get in the roller coaster, you clip in, you tick, 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 and you go up the hill. Generally speaking, that one hill, should be enough to take you through the entire rest of the roller coaster. Sometimes you need to have another one of those massive hills, but there is always one, at least one biggest hill. And at the top, at this location right here, what can we say about the different kinds of energy that you have? In this case, we're not talking about springs. It's going to be gravitational potential or kinetic energy. Those are the two that we talk about. If it's the highest peak, you can be even more specific than that. There is going to be a lot of potential. It's going to be, sorry? Very little kinetic. You're going to have a lot of potential. And at the tallest point on the roller coaster, you can say more than just a lot of potential energy. It's going to be the most at any point on this roller coaster is going to be right here. You're going to have the most amount of potential energy. So we're going to call the potential energy gravitational here some maximum value. Don't know what it is because we don't necessarily know what that height is. We don't know the mass of the person. We don't know how high they are up. But at the highest peak, it's going to be a maximum. And Lena said very little kinetic. I'm going to go so far and to say that the kinetic energy is, I'm not going to use an equal sign, I'm going to use an arrow. That arrow means it's not equal, but it's approaching. And I'm going to say it approaches 0. The language we use to suggest that the roller coaster's kinetic energy has approached 0 is, and the language you'll see in the problems, are things like barely, that word barely, makes it to the top. Means at this point, your kinetic energy is functionally 0. If this highest peak has the maximum amount of potential energy, then effectively what we've done here is, I don't know if this is ground level, but what we can do here is we can say that this height, whatever it is your 0 height. And this, whatever it is your max height. Again, not necessarily ground level, but as far as the drawing goes, that's what we would call your 0 level height. As you ride the roller coaster. At this stage, potential energy and kinetic energy have done what? Kinetic energy has gone up because potential energy has gone down. If we ignore friction, if we can ignore friction, the sum of these two values, your potential and kinetic energies, are going to equal what? If there is no friction, there is no work being done. So this is energy added or removed. This work term is energy added or removed. If we ignore friction, there's nothing being removed here. If we ignore, so I'll add something in here. If we ignore friction, there's no work. Lena, what did you just say? The sum of these is going to be the same as the sum of these. It's going to be whatever this, if I add these two together, we're going to get this equal to whatever this maximum energy was before. If we can ignore friction. If we can't, then the total amount of energy is going to decrease. And in a perfect world where you want your riders to leave a roller coaster safely, this is good. We want friction to take some energy out of the system. At the bottom here, what can you tell me about the different kinds of energy? You bet. Again, if we ignore friction, potential energy is equal to 0 because all of this potential at this stage has turned into the maximum kinetic energy. At this stage here, what can you tell me about PE and KE? Even vaguely. Okay, sweet. Both more than 0, less than max. But they both still add to that maximum value. Again, ignoring friction. Really great, terrifying roller coasters will take you underground. So let's say this continues. The track goes underground. What can you say about the potential energy and kinetic energy here? Yeah. You're going to have negative potential energy. And your kinetic energy is going to be what? More than max. But if your potential energy is negative and your kinetic energy is higher than the maximum, the sum of these is still going to be what? It's still going to be, they're still going to sum to the maximum available energy. And so energy is arbitrary. Like calling this height equals 0 and then having the roller coaster go below, having negative potential energy doesn't make sense. Having a kinetic energy that was more than what was available at the beginning, again, doesn't make a lot of sense. But if you consider the sum of these, and that's what's really important here, for all of this, as long as the sum of the energy does not exceed this maximum value, your system makes sense. Even if there's particular locations within the system that are going to be kind of weird. In a perfect world, if we're going to analyze this h equals 0 should have been at the lowest point of the roller coaster, whatever that is. You guys didn't know I was going to draw the thing going down a hill underground. Okay, let's look at some questions that have specific values. Flip the page when you're ready. I want to give you guys some time to work, so let's see how quick we can go through these. We have a 56 kilogram diver. This person runs and dives from the edge of a cliff into the water, which is located 4 meters below. If she is moving 8 meters per second the instant she leaves the cliff, find the speed at which she enters the water. This question sounds an awful lot like what kind of question? A kinematics projectile motion style question. Here's what's happening. Here's your cliff. Oops, that's not what I wanted to do. Sorry? She's not going to die. There's the cliff, there's the water. Here's our runner. Got some speed lines. She's going to go flying off the cliff. This is terrible form for a cliff jump, by the way. You do not go head first off the cliff jump, but she is. Maybe she will die. And she's going to impact the water below somewhere. We could solve this using kinematics. We've done that before. We'd break this thing up, we'd have x's and we'd have y's. We'd say that v equals, it's a horizontal, equals 8, vi equals 0, acceleration equals negative 9.8, acceleration on this side equals 0. We know the height of the cliff is, what is it? 4. So we know that the vertical displacement is going to be negative 4. We could do it that way. We could. But that sucks. Kinematics. We can use energy now to do the same kind of analysis. So let's take a look at energy. Using energy, the work energy theorem, everything starts here. Energy initial plus work equals energy final. It makes no mention of it, so we can ignore it. We're going to ignore air resistance. If she were parachuting, we couldn't ignore air resistance. But small heights, slow speeds, we can ignore air resistance. So energy initial plus work equals energy final. Because we're ignoring air resistance, work is equal to 0. As she leaves the top of the cliff, what kinds of energy does she have? Kinetic and gravitational potential. She's moving to start the problem, and she's above some height. There's no work done because we're ignoring resistance, and she's not wearing like a jetpack or anything. At the end, when she impacts the water, what kind of energy does she have? If we say that the water level is 0 height, what kind of energy does she have at the end? Lena, did you say something? Just kinetic. And so now we can use our expressions for kinetic and potential energy, and we can fill this thing in. We're going to have 1/2 mv initial squared plus mgh equals 1/2 mv final squared. This is interesting. In kinematics, I justified to you guys that mass didn't matter because it doesn't matter how massive the object is, gravity works on it the same way. Acceleration is always negative 9.8. Nowhere in kinematics do we care about the mass of the person. And if you look at energy, mass shows up in each term. So ignoring air resistance, we can actually cancel these masses. As soon as we bring in work, we cannot do that because there's no mass in the work term. But right now, ignoring air resistance, we can cancel those masses. So we're going to have 1/2. Her initial velocity was, where is it? 8 squared plus 9.8 times 4 is going to equal 1/2 her final velocity squared. So this is actually relatively easy to do. 8 squared is 64, and half of 64 is 32. 4 times 9.8. 4 times 9.8 is 39.2, plus the 32 we're going to get here. Multiply that by 2, square root that thing, and we're going to find that she has a final velocity as she impacts the water of 11.93 meters per second. So analyzing this same equation or same problem with energy, so much easier than doing it in kinematics. Questions about what I've just done? Okay, let's do another. A car of mass 1,500 kilograms has a velocity of 12 meters per second, and it accelerates to 25 meters per second. What is the work done? Well, here's what we've got. Car, it's moving. Now it's moving more. The speed lines have gotten bigger. To find the work, we could use kinematics for this. I've got an initial velocity, I've got a final velocity. We could use the initial velocity and final velocity to find the acceleration. Then we bring it over to dynamics. We take the acceleration, we multiply by the mass to figure out what the force was. We could go back to kinematics and figure out the distance that this thing accelerated for. We could use the force and the distance from dynamics to calculate the work, because work is equal to a force times the distance. We could do all that work. It would look like this. I'm not going to do it all. Kinematics to dynamics. Dynamics. Back to kinematics. Then out to work. It's doable. But the work energy theorem makes this so much easier. I've got energy initial plus some work done is equal to energy final. Now, we cannot assume that work is equal to 0 because the question says, what's the work? So to start the problem, our object is moving. The ground doesn't, as far as we know, the ground doesn't change. So the only kind of energy we care about at the beginning is what? What kind of energy does our moving car have? Kinetic. So KE initial plus whatever work is done by the engine is going to equal to your kinetic energy at the end. Well, I'm going to have 1/2 mv initial squared plus work is going to equal 1/2 mv final squared. We cannot cancel masses here because there's no mass in that middle term. So this is going to become, I'll plug it in here, 1/2 times the 1500 times 12 squared plus whatever work is done is going to equal 1/2 1500 times 25 squared. This is going to be a value. This is going to be a value, and I want to solve for work. So whatever this number is, I'm just going to subtract it over to the other side. If you are able to successfully do that. What value are you getting for the work? How much work is done by the engine to make this happen? Let me know when you've got a number. Alexis, you got a number? You betcha. 36,750 joules of work. Again, ignoring air resistance. So you have a perfectly aerodynamic car somehow. But if you can ignore air resistance, that's the minimum amount of work required to accelerate a car. And where's that energy coming from? Assuming you're driving a conventional gas-powered car, that's the energy stored in the bonds of the gas molecules getting released to do that work. Cool, next one. I've got a roller coaster question again. We want to find the speed at the top of the second hill. How fast is a roller coaster going at this stage, given the fact that at this stage, barely over the top of that hill, it's going 2 meters per second, and that hill is 20 meters tall. There are 2 ways to handle a problem like this. I told you guys, and I tried to justify right at the beginning when we were talking about gravitational potential energy, that you can dictate wherever you want your zero height to be. So if this is the question that you're given, where does your gut tell you to plug or to put 0? What makes sense to you? Where do we want to call 0 height? Don't just look at Lena. Like there's not a wrong answer to this. Where do you want to put 0? You have to define 0 somewhere. You want to put it at the bottom, okay? Makes a lot of sense, right? Everything is measured from this point. The arrows go down to that line. We could call height equals 0 there, no problem. If we do that, what kind of energies does our object have at the top? Well, we're some height above 0, so this thing has to have gravitational potential energy. And it's moving, so it's got to have kinetic energy. At this stage, again, we're still at some height, so we're going to have potential energy again. We're going to have kinetic energy, because presumably it's moving. We're asked to find the velocity. And if they don't say it in the problem, we can ignore all of the resistances. Air resistance, friction, all of it, ignore it. Unless it's mentioned specifically, we can ignore it. So if we do that, everyone's dying. We're going to have our work energy theorem is going to look like this. Energy plus work equals energy final. We're going to have PE initial plus KE initial. That's gone. Is going to equal potential energy final plus kinetic energy final. That's what the expression would look like if we put height at the bottom. But I tried to justify to you guys at the beginning of this chapter that it's arbitrary. You could put 0 wherever you want. Does anyone see another location that we could put 0? Sorry, where? You want to put it right here? Okay. At this stage, if we put it here, this potential energy would be gone. This potential energy would end up negative. We could, but there is a best choice here today. If we put the top of the lower hill as h equals 0, because we don't care what happens in between, all we care about is the difference between these two. If we put this here, what does that do to our potential energies? I still have potential energy here because now I'm not 20 meters above. This is going to be 8. And now this level is what we're calling 0. So there will still be a potential energy here. There's still going to be a kinetic energy here. But what happens over here? This is gone. The kinetic energy we can just find. So Liam's suggestion to put it down here at the bottom makes perfect sense. No reason why that's a bad idea. Lena's suggestion to put it at the top, a little confusing. Like conceptually, having negative, but again, mathematically, totally valid. But that idea, getting rid of this potential energy by putting it up at the top here, I think Lena, as soon as you said it, I saw it in your eyes that you knew what I was going to say. Putting it at the top of the lower hill gets rid of the potential energy term at the end. It allows you to go straight for the kinetic energy here. This makes perfect sense, but it's more work. If you put the potential energy here, what you're going to have is your initial energy plus work is going to equal your final energy. The work is 0. We're still ignoring resistances. Your initial energy is still potential and kinetic, but it's only going to equal kinetic at the end. You can do a little bit less work with an unconventional placement of 0. Because I mean, if you're standing outside looking at a roller coaster, it doesn't make sense why you'd call this 0. Unless you're looking at it through the lens of, I have a bunch of math to do. Let's ignore a bunch of it by calling that height up there 0. And then all I care about is the difference between the highest height and that height. I'm not actually going to go through and do the rest of this calculation because I think we could do that, and I want to give you guys some time to practice this stuff. Are we cool if I ignore the rest of this question? Because the reason I wanted to put it, oh yeah, right. The only other note that I'm going to make here is this thing, that potential energy is no longer measured, not measured with H equals 20 anymore. It's the difference in Hill heights, which we already we suggested over here, but I want to make that really clear. If you're going to start arbitrarily moving what we call zero, and there's values listed in the problem, you can't use them anymore. You have to make the change between them, which I think is the trade-off there is worth it, I think. 20 minus 12 is less work than doing this whole term and then having to move it around and all that kind of stuff. The math trade-off is worth it, I think. Not necessary, but worth it. Okay. Let's take a look at this guy here. We have a roller skate. Initially at rest on a frictionless table. And a 10 Newton force acts on it. The skate travels 3 meters while the force is acting. We want to find the final velocity. So this is what we've got. We've got a roller skate at rest on some tabletop, and the thing starts moving. Somehow it got bigger, but that's okay. It doesn't matter. It's moving because some force applied of 10, was acting on the roller skate over these 3 meters. We want to find the final velocity. Again, kinematics, we could do this. I know the applied force. I could use the applied force to find the acceleration. I could find the acceleration and the 3 meters and the initial velocity of 0. I could do all that and find a final velocity. Or we can use energy. Energy initial plus work. Everything starts here in this chapter. Energy initial plus work equals energy final. Is there any initial energy to start the problem? No. That's 0. Is there work being done? Be careful here. Sorry? We're told that it's a frictionless table. Sorry? So there's no friction work being done, but we're also told we have a 10 Newton force acting over 3 meters. So the friction's not doing any work, but this force is. Remember, work is equal to a force times a distance. So this applied force, so I'll make a note here, FA is doing work even though friction isn't. So when you see frictionless, it doesn't automatically mean work is 0. You have to look at what else is happening in the problem. Because we've got an applied force, we have a different force doing work. Now all of a sudden we've got work being done. So all this means here is that we're going to have a force times a distance giving us kinetic energy. So we're going to have a force times a distance is going to equal 1/2 mv squared. And we could plug all this in. But for the sake of time, I'm not going to. This is, I think, from this point forward, I think you guys are good. If you want to go test this on your own, you're looking for a final velocity of 5.5 meters per second. And I've got one more kind of problem I want to look at before I release you to do a whole bunch of practice. We have students going to Ravine Park. Don't go to Ravine Park. But you do. Several students are pretending that they're in the jungle while playing in Ravine Park. They suspend a rope from an overhead tree limb. A student of mass 70 kilograms running at 8 meters per second grabs the rope and swings off the ground. What is the maximum height the student reaches? So let's draw this. There's the ground. Here's the tree. Somehow, I don't know, we nail a 2x4 to the tree. We hang a rope. And we take a really fast student. And they run at the rope. 70 kilogram mass student running at 8 meters per second. They grab the rope, and what's going to happen is all of that kinetic energy is going to get transformed as they rise. It gets transformed into gravitational potential energy. And so you're going to have a person, they're going to be hugging the rope here, and they're going to rise to some height above the ground. That's what we want to know. So, all energy. Energy initial plus work equals energy final. If it makes no mention of air resistance, we can ignore it. It doesn't say anything, so this work term here is 0. There's no applied force, there's no friction, there's no air. This is 0. So then to start, we've got kinetic energy. At the end, we just have potential energy. So kinetic energy initial is going to equal potential energy final. So I'm going to have 1/2 mv squared is going to equal mgh. Are there any mathematical simplifications we can make here before we plug in any values? The masses cancel. And now we can plug stuff in. We're going to have 1/2 8 squared, because they're running at 8 meters per second, is going to equal 9.8 h. I'll give you that value. It's not a hard calculation. You're going to get 3.27 meters, which is right around 10 feet. Person gets pretty good. Swing. We're ignoring air resistance and friction because it doesn't say anything about it in the problem. Person's at ground level. We want to know the height they rise to. So it makes sense to call this level 0. They only have kinetic energy, and at their maximum height, they no longer have any speed. So we went through and we solved it. We found I went through ahead and solved it. 3.27 meters is the maximum height. How fast would a 60 kilogram student have to run to reach the same height? Sorry, Lena? Lena says faster. Is she right? Girde says slower. Gernavin? We have all 3 options. Faster, slower, same speed. Why, Gernavin, are you suggesting the speed doesn't matter, or the speed is the same? This wasn't just for a mathematical simplification. I was making a point here. Because the masses cancel at this stage, speed remains the same. It does not matter what the mass of your person is. If my 4-year-old daughter could run at 8 meters per second, she would go 3.27 meters above the ground. If Fuj ran at 8 meters per second, he would go 3.27 meters above the ground. It does not matter the mass of the runner, as long as they're able to hit 8 meters per second, that person, whomever they are, is going 3.27 meters above the ground, which is obviously not intuitive because we had all three options, faster, slower, and the same. But the math is beautiful. There's a reason why here day I had you cancel those out. Love it. Okay, so at this point, I'm going to free you to practice. Here's what I want you to work on. I've got a list of questions that I want you to take a look at here. It's not going to be all of them, and there's a second page back here that you're going to look at. I want you to do the questions, write these down, 3 to 5, 8, 9, 12, 13, 2, 3, 5, and 6. So just so there's no confusion, this 3 to 5, 8, 9, 12, and 13 is off the first set of questions, the energy calculations. Then I gave you a list of questions right here that are all about springs. The numbering restarts at 1. So I want you to do 2, 3, and 5 here. There is no question 6, so you're going to have to flip the page. Off this page here, Law of Conservation of Energy Problems, I want you to look at question number 6. So there's 3 chunks of questions. Those are the ones I want you to take a look at. You've got somewhere in the neighborhood of 15 minutes. You can make a reasonable start on this stuff. If you'd like some scrap paper, you know where it is. Otherwise, you've got your own and on your market say giver. Tomorrow, if you flip the page, we will be doing our bungee. We'll be starting our bungee. So the only thing you need to do, well, the other piece that I want you to do for homework is I want you to read through this. Read through the lab so that you have an idea of what tomorrow and part of Thursday are actually going to look like. You'll be working in 2s or 3s. So perhaps today before you leave, figure out who your partners are going to be for the bungee egg jump. If you know you're going to be absent tomorrow, don't agree to work with someone. Oh, dang. Because you're going on a Whistler, aren't you? Shoot. That's okay. By the printer. And it's not actually scrap paper. It's pristine paper. Straight out of the box. But you're using it to do your work. Yeah, you're gone all day tomorrow, aren't you? Dang, that's a... You could just skip the field trip and come to physics. Okay, so Lena's gone. Before you leave today, figure out your partners. Reading this is part of your homework. Sorry? 2s or 3s. Partners or groups of 3s. We do have an odd number. We will have an odd number of people here. Figure that out before you go. This lab, yeah, it's good. It's a good one. And there's your task.